this is all contained in UAG 1.12. So I'm writing here the space of quadratic forms in XYZ. So this is a 6-dimensional vector space. And then here, at each of these points pi, I'm saying I want the quadric to pass through this point. And so I'm writing down the quadratic form, evaluated at some point, and then saying that should be equal to 0, and that is a linear condition on the 6 coefficients here. So I start off with a 6-dimensional vector space, and then I write down conditions one at a time. So I say I get a vector space of dimension 6 minus n. And that's true except that I haven't told you the condition. I haven't told you the exception. So can we find an exception first? So for example, if I have 4 points, P1 up to P4, can it happen that QPI equals 0 for all I equals 1 up to 4 is only 3 conditions? So can this happen? So there's a little hint here. So let's just consider this: P1, P2, P3. Suppose it happens that 3 of my points are collinear. Then I say quadric at these PIs equals 0. That means that the quadric, the conic intersect this line has more than 3 points. Okay, so is this possible? So in the last lecture I said I take this quadratic form, I restrict it down to the line L, and I must get a quadratic form in the 2 variables. So this is a quadratic equation that has 3 solutions. Right? So what does that mean? I write down a quadratic form and it has 3 different solutions. Means that it's identically 0. Right? So this is so a quadratic form restricted to L is quadratic with greater than or equal to 3 zeros. Right? And of course, if this is a non-trivial, if this is not not 0, this is a contradiction, right? Because when I was talking about Bezout's theorem in the previous lecture, I said that Q insect L is degree of 2 times degree of 1 is 2, possibly with multiplicity, but there's no way I can't get this. So that means that this means that if 3 of my points are collinear, I impose the condition, and each of them is a linear condition. So maybe I've imposed 3 conditions. However, having done that, So in other words, S of P1, P2, P3, this S2 of P1, P3 consists of quadratics that vanish entirely along the line L. So in other words, they look like this. Here's L, here's some L prime, and Q equals L plus L prime. So this is if P1, P2, P3 are on L. Yes? So it's a completely basic result of algebra that if I've got a polynomial in one variable of some degree, then it has at most that number, that degree of zeros. So here I have a quadratic polynomial that has at least 3 zeros. Therefore, the quadratic polynomial must be identically 0. So this means that Q is identically 0 on L, and that means that Q is of this form. Right? So how many of these are there? If I fix L, how many are there? If I fix this is L times X, L times Y, L times Z times L. So it's L times any of these linear forms. So, this is still 3-dimensional vector space. So in other words, I impose these three. I've imposed 3 special points. Point special here, collinear. Right? And it does give 3 linearly independent conditions on Q. Right? So it cuts down the whole of S2 down to the guys in S2 that are multiples of L. So to be a multiple of L means exactly this. Right? So having 3 points collinear, does not contradict this thing. Right. But what about having 4 points collinear? So if I have P1, P2, P3, and then I have some other point here, so R or something, then imposing. So I require zeros at these 3 points. Impose P1, P2, P3, and you get R for free. Yes. So here I'm imposing these points here, P1, P2, Pn. So I told you for fixed Pi, imposing this condition gives imposing this point, requiring that the conic should pass through this point, is a single linear condition on the quadratic, on the coefficients of the quadratic. Right? And so here I'm saying I impose the points P1, P2, P3, P4, P, and so on. Then I'm imposing one condition at a time, and so I should get 6 minus n. Right? But here, what happens is that I impose P1, P2, P3, each of those is one condition. However, once I've done that, the condition for R is trivially satisfied, is identically satisfied. Right? So in other words, the linear condition for R is linearly dependent on the condition for P1, P2, P3. Right? So in other words, what I need to write in this result, I need to write, so except, sorry, this board is getting a bit messy. Let me try and write it more cleanly. So it's a proposition. So P1 up to Pn are points of P2. So I'm looking at S2 of P1 up to Pn is the quadratic forms vanishing at Pi. Yeah, so that's just the definition. So I say assume that n is, let me say less than or equal to 5. We can argue about 6, but let me say less than or equal to 5. And that, and so I'm going to make the condition here, no 4 points of Pi are collinear. Then dimension of this S2 P1 up to Pn is 6 minus n. Okay, so in other words here, it's possible to miss this number. It's possible to have something bigger than this. Namely, if 4 of the points are collinear, then I'm going to get strictly bigger than this. Okay, so let's prove this. So how do I prove it? So let's assume n equals 5. So suppose that dimension of S2 of P1 up to Pn is greater than or equal to 5, greater than or equal to 2. Right? So I'm trying to prove that this is 1. So by contradiction, assume it's greater than or equal to 2. Right, and so then in there I can find Q1 and Q2. And so now I can start talking about geometry. Now I can draw these. Kind of pictures. So then I've got, if Q1 is non-degenerate, then I get some picture like this, and then this, this is Q1, and then, I don't know how to draw Q2 anymore. It's impossible to draw Q2. And Q1 intersect Q2 is less than or equal to 4 points. This is by the easy Bezout. Right? So I said earlier, I said earlier today, in the first lecture today, I said if your Q1 is non-degenerate, then I can think of this Q1 as being isomorphic to P1. I can think of the equation of Q2, whatever it is, as a homogeneous quadratic form. When I restrict it to Q1, it's only allowed to have 4, at most 4 zeros. Right, and this is a contradiction. So therefore, Q1 is something like Q1 is degenerate. Right, but I'm still not completely finished. Then, so for e.g., for example, suppose that Q1 is L1 plus L2, 2 lines. Right, then Q2 is somewhere. I do Q2 intersect L1. So I do if I do Q2 intersect Q1, this is Q2 intersect L1 plus Q2 intersect L2. And this is a problem we already discussed. This is a line and this is a quadratic. Right? So there's at most 2 points here and at most 2 points here. And so again, this is impossible. So how do we get out of this? So one of these sets has to have at least 3 points. And that means, exactly the argument I had over there, that means that the Q2 must contain L1 or L2. Right? So this implies that Q2 contains L1 or L2. So the argument is here, it's impossible for Q1 to be non-degenerate, therefore Q1 must be degenerate. A degenerate conic in the plane is either 2 lines like that, or 2 separate lines, or it's a double line. So this is the only serious case. So suppose that Q1 is like this, and we still have to have Q2 intersect Q1 contains 5 points. So this union of 2 sets contains 5 points. One of them has to have at least 3 points, and that implies that Q2 contains L1 or L2. Right? So if Q2 contains L1, then Q2 is L1 plus L3, maybe. So here is Q1, and here is Q2. So Q1 is all of this stuff, and Q2 is all of this stuff. Right, and then what's the intersection of them? Well, it's this line together with 1 point. And my set, this has to contain this intersection of 5 points. So here I have so Q1 intersect Q2 has to contain P1 up to P5. Right? But that means that, 4 of them must be on L1. Okay, so this is a very simple argument. I've imposed 5 linear conditions on these 2 quadrics. So in the normal run of events, those 5 conditions ought to be linearly independent. If they're linearly independent, then I can't have 2 quadrics. So assume they're not, then I get 2 quadrics. Intersection of 2 quadrics is 5 points. It contains 5 points. So, we say, well, that's impossible. The intersection of 2 quadrics is at most 4 points. So this is the argument that I had earlier in the day, earlier into the first lecture today. Right, so if Q1 were non-degenerate, then I have at most 4 points. Right, and so therefore Q1 is degenerate. But it's degenerate, then where are those points? Well, the Q2 has to contain either Q2 intersect L1 or Q2 intersect L2 has to have at least 3 points. There are 5 points in here. There are 5 points in here, and so one of these 2 has to have at least 3 in. Right? And that means that, for example, Q2 contains L1. right? So if Q2 contains L1, then it means that Q2 is this shape. So, you know, the intersection of this curve and this curve consists of this whole line together with just one single other point. So my 5 points, only one of them can be this point, the other 4 have to be somewhere there. Yes? And so this is this is the contradiction. This contradicts the assumption. Okay. So I want to move on to another topic, but let me. I set this. So one of the examples on the example sheet, I don't have a copy of it, so I don't know if it's number 3 or number 4, is write Q1, Q2, so that Q1 intersect Q2 has multiple points. Right. So one of the pictures in the book looks like this. Here are 2 quadrics, and they intersect like this. And what I'm saying is here. So here is Q1. It's a non-singular quadric. I want Q1 intersect Q2 to be this point here with multiplicity 3 plus some other point R. So you know, you're used to drawing ellipses, especially the way geometry is taught nowadays. If you draw an ellipse, then you have to be able to draw it on a computer screen, so its axis is always horizontal or vertical. So you look at that picture and you say, is that really possible? So so I want to give a hint, just a hint. I'm not telling you how to do the exercise, I'm just giving you a hint. So is this possible? Well, you know, it looks pretty silly, doesn't it? On the other hand, you know, I've got my two ellipses here, and I can. So, you know, here's an ellipse, here's a point on it, and then I can, you know, it's got a tangent line. So I can take 2 of these guys, and I can line them up there so the tangent lines are the same. And I can do that, and the 2 curves are not identical, right? And unfortunately, this is sort of pretty unlikely. So let's play around with this one, move the center of, you know, move the curvature at this point to be slightly bigger or slightly smaller so that the 2 guys cross over. So I hope that what I'm saying is completely implausible. In other words, I hope you don't believe it. So, on the other hand, here's something. So, you know, in other words, you try to do, this is a problem in geometry. I'm asking, can you find 2 conics that intersect like this? And trying to do it in geometry is going to give you a headache. Right? It's going to be very difficult, and at the end of it, you still won't know whether it's true or not. You won't know whether to believe it. On the other hand, here's an easy, so, you know, formal algebraic. Approach. which is, you know, let's not try to be too geometric about things. Let me just draw this picture. So this is one of my conics, right? And here's the second of my conics. It's like this. So here's Q1, and here's Q2 is L1 plus L2, where L1 is a tangent line at P, the tangent line at P. And L2 is some other line through P. So if I do this, the thing that's completely clear is that the intersection of Q1 and Q2 takes place only at 2 points. Right? There's that line there that cuts through the ellipse, so it meets it in 2 points, and then there's this tangent line there, and that tangent line only touches it at this point. Right? So then, if I do Q1 intersect L1 plus L2, this looks like 3 points at P. The point P counted with multiplicity 3, and then some other point R. Right? So I haven't quite got this picture, because in this picture I want Q1 and Q2 to be non-singular. Right? But if I do Q1 plus, I do Q2 plus lambda times Q1, then, you know, I'm just moving this singular guy in a linear system, and, you know, his neighbours will certainly be non-singular, right? But the intersection hasn't changed, because if Q1 is 0, it's not changing anything there. If I take this and I restrict it to Q1, then I'm getting the same as L1 times L2 restricted to Q1. So that's a hint to how to do it. And, you know, if you're clever at, for example, computer algebra, then maybe you can draw this picture so that the two ellipses are not vertical things. They're slightly skewed vertically, and they're just the right degree of skewedness so that they... So, you know, if you take a small deformation of this, you'll get something like this. You know, this is not exactly what you normally think. Okay, it's not a very good picture. Anyway, this is a hint as to how to do that exercise on the sheet. So, you know, actually writing down completely explicit equations here and checking that Q2 restricted down to the equation of Q1, Q2 restricted down to the equation of Q1 is 3 points P plus 1 point R is just an exercise now. So this is the idea, and you have to do the calculations. So I want to go on to a topic in cubic curves. So this is already a much bigger subject. So I want to talk about C3 in P2 and its geometry. And so this is really a big subject. So let me say non-singular C3 is an elliptic curve and straight away you get into one of the major topics in modern number theory. So I'm going to explain this thing. It has a group law. In other words, this is a geometric object. This is a curve in the plane. So if I have to draw it, here's my P2, and here is my curve. It has a group law. So this is C. In other words, I fix 0 in C, and then there's a multiplication C times C to C, which is an abelian group. It has a normal form. It has a normal form which is y squared equals x cubed plus ax plus b, or it's y squared z equals x cubed plus ax z squared plus b z cubed. So this one is in affine space. I don't know if I introduced, this is the same as K2 with xy. In P2 K with coordinates x, y, z. Okay, so I say I'm going to study cubic curves in P2. Then here are some of the main results concerning it. I'm just stating it at the outset to say it's an interesting topic. Possible to give it a rational parameterization. So this will take me most of Thursday's lecture to talk about. So I'm not going to do it all immediately. So how do I want to start this? So I discussed earlier I can do P1 and I can map this to P2 by doing UV maps to u squared uv v squared. Right, and so the image is C is the image is Q is a conic. Is a conic Q, and in fact it's the conic x z equals y squared. Right. So what happens if I do UV maps to, suitable cubics, some cubics? Well, this is actually something that is fun and interesting to do, but the thing that's interesting is that this is always singular. Right. So let me draw the singular cubics, and let me draw them in sort of a choice of coordinates. So here's one guy. So let me choose this. Y squared equals f3 of x. And let's suppose that f3 of x has a multiple root. Right. So if I write not this equation, if I write the equation, let me say eta equals f3 of x. Right. Then here's the x and eta plane. So let's sort of think of this as x cubed with a 1 here, plus ax plus b. Right. So what does it look like? Well, you know, it looks something like this. Yes, or possibly something like this. So if I'm drawing the real locus of this curve, then what I have to do is I have to take the square root of the thing on the right. Right? And so the square root will only happen here. Right, so in this case, what I'm getting is a picture that looks sort of like this. No. The pictures in the book were done in computer graphics, so they're accurate. I mean, they were done using explicit calculations, and then here I have some picture like this. So here I'm taking the square root of this picture. Right, here I'm drawing the xy plane. Right, and where this function is positive, then there'll be two roots over it. Where this function is 0, there's exactly one root, and where this function is negative, where f is negative, there'll be nothing. So I get a picture that looks sort of roughly like that. So in this case, I get, you know, nothing here. I get two complex imaginary numbers here, and then here I'm going to get sort of thing like this. Right, so these are the non-singular ones. If f3 has two distinct roots. So I will prove that I will prove later that these non-singular guys, these non-singular curves, are certainly not the image of a parameterization. So which ones are? So let me draw some singular ones. So how will it happen that this is? So to get singular C, I'm going to let f3 have a multiple root. Right, so here's again, let me draw this plane slightly bigger. This is the x and eta plane. So I want this function, so this is the function eta equals f3. I'm drawing a graph of eta. I want that to have a repeated root. So here's one possibility. Right, and here's another possibility. So what does the curve look like in this case? Well, in this case it looks a bit funny. It looks like this, and then a single point here. So is it really possible that this is a curve? That I've got a curve here, and it has a single point here. So this is a singular cubic curve with isolated point. So what kind of curve is it that has an isolated point? So the thing is, it's an isolated point because the picture is in R2. If I were to draw the picture in C2, what I'd be seeing is two complex imaginary curves coming in there, just ordinary nice non-singular branches, but meeting in a point, right? So this, whenever you see an isolated point of a real curve, it means in the complex picture there's something more interesting going on, right? So what's happening here is much more geometric. So here let me draw it somewhere like this, right? Here I'm going to get a picture like this. So here I'm writing down y squared equals f3 of x, where x has a multiple root, f3 of x has a multiple root, has a double root, that is a local minimum. So here I'm drawing the picture, I'm drawing the graph eta equals f3 of x. So at a place where there's a double root there, where f has a double root, it means that f is 0 and also f primed, the differential of f with respect to x is 0, right? And that means that the tangent at the bottom of the curve is 0, and that means that I'm either at a local maximum or a local minimum or at an oscillation point, right? So here this is a local maximum. Right, and then there's another point where f3 has a triple root at one point. So here's f3. Let me just write a picture like this. So if f3 of x has x, well, it might be x cubed, for example. So if this is the picture that's drawn here, if I take this to be x and this to be eta, then this is a point where f equals df by dx equals d2f by dx squared equals 0, and d3f by dx cubed is positive, right? So I might as well just take f to be x cubed. So if I do that, the curve doesn't exist over there at all, and over here it exists in two branches, and these two branches sort of tend together like that. This is called a cusp. So this is called a node, and this is called an isolated point, right? But an isolated point is really also a node over C. So let me write down explicit equations here. So what are we going to do here? Should we take this to be 0? So let me say that that f here is x squared times x minus 1. right, then if I take x squared times x minus 1, then it's near x equals 0. If I'm in the neighborhood of x equals 0, this looks like minus x squared. Right? If this x is very small, if the x is very small, then this looks like minus 1, and this looks like minus x squared. Right? And then it has a single root here at x equals 1. And here, in exactly the same way, I can do this. So I'm going to take this to be the origin of coordinates, and this to be eta. So here I'm going to take f is x squared into x plus 1. Right, and here I already told you I'm going to take f equals x cubed. So these curves, these singular curves, have a rational parametrization. So this one is the easiest. So if I set x equals t squared and y equals t cubed, right, then what, so I'm doing, this is affine coordinates. I'll tell you how to do it in projective coordinates in just a minute. Right, so here's the t line. It's getting mapped forward into the xy plane. So this is K2. Right? Obviously, the origin there is getting mapped to the origin. Everything is being mapped to the positive half plane. Right? This x is always going to be positive. So this ends up being something like this. Okay, so now let's do this. Now let's do this projectively. Let's do this as P1 maps to P2. Right, and I'm just going to take this to be UV, and I'm just going to map this forward to U cubed, and then UV squared and V cubed. Right, so if I start off with these equations, obviously I'm going to end up with y squared equals x cubed. Right, if I do this, then I'm going to get z y squared equals x cubed. I better tell you which is x, y, and z. Yes, okay, this is a good question. This one better be x. So I want this to be y squared. Okay, this is y and this is z. Okay, so in this case, this picture here is the affine picture. This is the picture in ordinary straight, the t line and the xy plane. And so this is when z equals 1. So you get right. So if I go back and I just set u equals 1, then I'm just getting back the original picture here, and z equals 1. Okay, so let's see if I can do the others in the same way. So which of these am I going to look at? This one's the nicest one. So y squared equals x squared times x plus 1. So what's one way of thinking about what's happening here is I'm trying to take the square root of x squared times x plus 1. Right? And, you know, this is basically a silly thing to do. Better take x times the square root of x plus 1. So if I'm taking the square root of something, you know, if I ask you what's the square root of 28, what's the square root of 28? So you think for a bit and you say, aha, 28 has got 2 squared in it, so I already know how to take the square root of that. Let's take that outside. So, you know, square root of 28 is 2 times the square root of 7. And this is a simpler expression than this one. So it's the same, it's basically the same thing here. So if this were the equation, so you know, let's sort of think y primed equals y over x. Yes? Then y primed squared equals x plus 1. And you know, I've changed the curve a bit. So this is a parabola in the x, y primed plane. Yes, and so in principle we know how to parameterize it. So when I say we know how to do it, it means that I can figure it out if I spend 5 minutes, and I can set it to you as homework. Right? So one of the homework questions is sort of basically similar to this. You know, the way to parameterize a plane conic is to find a point on it and to do all these lines out of it. Think of the, you know, this lambda as the slope, and then this point here is a rational function of lambda. Anyway, of course, we can do this much more easily than this. Let me just, I want to, what happens if I do x is I may get this wrong. What did I do over there? X is t squared, y equals t cubed. Let's do x equals t squared minus 1 and y equals t cubed minus t. Right, then t is y over x. So x equals t squared minus 1 is y squared over x squared minus 1. And so this means that x cubed plus x equals y squared. Okay? So in other words, I'm starting from this and I'm saying let's perturb it a bit. You know, I can think of this t squared minus epsilon, t squared minus a little change, and then this is t times the same thing. Right? So the picture here is the t line, and it's mapping forwards into this picture, where this is x equals 0, y equals 0, and then this is, you know, am I doing this right? When t is 0, y is 0, and x is minus 1. So this is the map phi. It's taking t maps to t squared minus 1, t cubed minus t. And so then I think the 2 points plus or minus 1, t equals 0 maps to this root here, maps to minus 1 comma 0, and t equals plus or minus 1 both map to the point 0, 0. Yeah? So, you know, and there's an issue that's going to come up later in the book as well, which is that there's a kind of inverse to this map. So let me write psi so let's take psi equals x comma y maps to y over x. So this is a map from curve C given by, what's the equation? Y squared equals x squared into x plus 1. So this is mapping from C back to the T line. Right? So this is taking this singular plane curve and it's taking back there. So, you know, what's its special property? So if x is not 0, in other words, if I'm not exactly at this point, then you can think of this map backwards, x over y maps to y over x, you can think of this as just the inverse of the parameterization. So if x is not equal to 0, this is the inverse of phi. Right? So what happens when x is 0? Well, when x is 0, this is, you know, the point we're talking about is 0, 0. So what's the value of y over x if both x and y are 0? Well, answer, we don't know. Right? So you're not allowed to, in mathematics, you're not allowed to write 0 divided by 0. Right? So here what's happening is that, of course, you know, if I was not actually at that point, but if I was just somewhere near that point, right, then this y over x would have a perfectly defined meaning, namely it will be plus or minus 1. So the two branches of the curve there, as long as I'm not actually at 0, the two branches map back there. Right? So this is what I mean by rational parameterization. Right, so this is the curve C, singular cubic. So the one I'm talking about is y squared equals x cubed. Is it minus x or plus x? Sorry, plus x squared. Has a rational parameterization. Namely, this t maps to t squared minus 1, t cubed minus t. With rational inverse, xy maps to y over x. So, you know, there's a sort of strange thing that's happening here. Maybe it's not strange to you, but it's strange to me. Namely, if I do first phi and then psi back, I'm doing t maps to t squared minus 1 t cubed minus t, and then I'm doing t cubed minus t divided by t squared minus 1. Answer t. So the composite, if I do the composite this way and then the composite back, I have the map t goes to t, so I have the identity map of the line. So the identity map of the line is, of course, regular at every point. Right? So here I have a map here and a map back, and the map back is not defined at this point. Nevertheless, the composite is perfectly well defined. Proper use of, this is improper use of language. This is an inverse that's partially defined. So where it's defined, so if I censor out, if I forbid you to look at this point and forbid you to look at this point, then the map there from the t-line without the origin to this curve C without the origin is, I'm sorry. I forbid you to look at these points, right? And I forbid you to look at this point. Then this is the t-line, take with the complement of plus or minus 1 on the t-line, right? I cut out those 2 points, I map it forwards, and that's a perfectly nice isomorphism, right? And then there's a map here which is not defined at the origin. So this word rational here is like the word meromorphic. It means that the function is not defined at some points, right?
Okay. What I wonder is the reason why we have, for this case, has inverse, rational inverse for the parameterization. So is it possible to always have some parameterization?
So you're asking a complicated question. There's a theorem called Liouv's theorem which you're asking about. So let me not answer it at the moment. So at the moment, the kind of parameterization I'm talking about is a parameterization which is one-to-one, except for one-to-one and regular, except for a finite number of points in both directions, right? And so here we're going to say, with exceptions, this is a regular map with a regular inverse, and the composite phi psi is the identity here, the composite psi phi is the identity here. We'll come back to this many times in the course. This is one of the difficulties of the course, one of the fundamental problems, headaches, that you have if you study algebraic geometry. Okay, so I don't have so much time to talk to the main result. So let me just indicate very, very quickly how we're going to... let me come back to this. So next time, the non-singular guy, the non-singular curve, has no rational parameterization. Right, so in other words, here is, you know, y squared equals f3 of x with no multiple roots. Then if I do a map from the t-line to the curve C, then the map is any map from the t-line to C is any rational map, any map defined by rational functions is the constant. Right, so in other words, here's the curve C. I would like to be able to draw it like this by drawing rational functions, by taking the coordinates, the xy coordinates of the point C are rational functions of t. And I might want to do it, but it's impossible to do. Okay, so that's the theorem I have to talk about. So let me talk about the group law, which is just, you know, there's a hard thing to prove, but there's a very pretty picture. So why a group law on C3? So let me come back to conics. For conics, the basic construction is projection from a point, is linear projection from a point in Q. For conic Q in P2, in Q, P in Q. Yeah? So here's a conic. Here's a point on it. Then if I take lines through, if I take the line through P with slope lambda, so we know how to write that down from coordinate geometry, then I take the equation of Q and restrict it, then I get P plus, so line lambda L, line through P with slope lambda, then it meets Q in L lambda intersect Q, which is the point P. You can't get away from that. We've already put that in, plus a variable point. So let me write R lambda. R lambda is a variable point. Right? And this R lambda, the coordinates of this R lambda are rational functions of lambda. So you already saw this in the equation of the circle, where you're writing down things like 2 lambda over 1 plus lambda squared, and 1 minus lambda squared over 1 plus lambda squared. So this is an example of this. And you'll do another example of this in the homework. Yes? So what can we do on a cubic? So, you know, this is a geometric construction. This is a projection. This is like stereographic projection when I try to make a map as a projection. So what can we do with a cubic? So we can't do this because, so here's my cubic curve. Let me draw him sort of sideways. Here's my cubic curve. If I draw a line, then line intersect to cubic will be, in general, we expect it to be through points. Okay, and you know, if I take all the lines with different slopes through the point P, if I try to copy this procedure, then I don't get 1 point for each value of lambda, I get 2 points. So this doesn't give a parametrization. In fact, I will prove that there isn't any parametrization. But what it does give is this, that this gives a binary operation P, Q maps to R. Right? So it's not the same picture as here. right? So here I fixed P and I chose any line through P with slope lambda. So here I'm doing something slightly different. Here I'm saying, let's take 2 points. The 2 points define a unique line, a unique straight line through point P. Now if I take, so PQ maps to the line LPQ in P2. So it's a line. And so if I do C intersect LPQ, this is 3 points. Yes? It's 3 points. So this is, as I explained earlier, this is a homogeneous cubic polynomial in XYZ. If I've got UV coordinates here, then this is take a homogeneous cubic in XYZ and restrict it to the UV line. And so I get a homogeneous cubic in UV, and so that's going to have 3 roots. However, I already know 2 of the roots, and so therefore there is a 3rd root, and the 3rd root is defined rationally. It's the 3rd root of a polynomial where we already know 2 of the roots. So this 3rd point, R, is the 3rd root of a cubic polynomial where we already know 2 roots. Yes, so that gives a 3rd point. So I can write R is P star Q. Right? And you know, there's a little bit of problem here when what happens if P and Q are, what happens if P equals Q, for example. Then I don't draw the line PQ, I have to draw the tangent line to the curve at P. But basically this works always. I'm assuming here the curve is non-singular, including at infinity. Right? So there's a binary operation that I'm sure you've learned abstract groups and all this stuff about associativity law and so on. So the group law is given by P plus Q plus R equals constant. So I'll explain later, explain next time. So this operation is of course not a group law. It's not a group law, for example, because a group has to have a 0 element, has to have an identity element, and this operation doesn't have any identity element. But if I change it a little bit by doing this, so in practice that means I fix some origin, and I do this. Anyway, I'll 0 star R. Anyway, I'll come back to this picture in the next 2 lectures. So this is, as I said at the beginning, this is the beginnings of the theory of elliptic curves. So if you do number theory, a lot of number theory is the Diophantine geometry, number theory. A lot of it is concerned with elliptic curves. So these are very rich. These are very rich in number theory as well as in algebraic geometry. Okay, so people want to ask questions. I'm quite happy to